Okay. Yes. So in the last class, we did equilibrium, and today we are going to discuss Haber process and contact process. Okay. So basically, this is equilibrium reaction, right? Um, in this process, nitrogen is going to react with hydrogen to form ammonia. Basically, you know, Haber process is a reversible reaction. So I told you reversible reaction means that when the dynamic equilibrium is established, so the rate of forward reaction is equal to the rate of backward reaction. So in this, I have mentioned that when reactant goes to the product, so this is called forward reaction. And when product goes to the reactant, this is called backward reaction. Okay, this is called backward reaction, right? Then, okay, uh, let's suppose we have, and we discussed this Lee-Chatelier principle, right? We discussed this Lee-Chatelier principle, okay? Concentration, temperature, each and everything we discussed. So yes. So whenever we are going to make something else, let's suppose you are going to make a tea, so you need some uh, preliminary data. Like let's suppose you need some milk, you need some sugar. Okay, so these are called raw materials. These are called raw materials, right? So you are going to form ammonia, you are going to prepare ammonia, so you need a raw material. I mean to say that you need nitrogen gas and hydrogen gas, right? So the thing is that what is the source of nitrogen? What is the source of nitrogen? Okay. So nitrogen can be obtained by the fractional distillation of air. This is the chapter that we would be discussing called environmental chemistry, air and atmosphere. Okay. In this chapter, we would be learning how can we distill air so that we can separate out nitrogen, and also we can separate out hydrogen, like nitrogen and oxygen gas. Okay, so and the source of hydrogen is electrolysis of water, decomposition of CH4. There are two methods by which you can separate hydrogen gas. The first one is electrolysis of water. Like electrolysis means when you are going to provide electricity to the compound, so the compound is going to be broken down into the respective elements that are hydrogen and oxygen, right? And the next method is the decomposition of methane. Decomposition is also the breaking down of any compound by means of heat. And also fractional distillation of air means that in air I have 70% nitrogen gas, 70% nitrogen, 78% nitrogen gas. So that's why we can easily obtain nitrogen gas by doing the fractional distillation of air. So once we got the nitrogen gas and hydrogen gas from their resources, then I would be able to let them react together and they would be forming ammonia. So basically, this is a chemical reaction. Nitrogen goes to react with hydrogen to form ammonia. So if you can see, this is a balanced chemical equation which shows that you have 1 mole of nitrogen and 3 moles of hydrogen, and they are going to form 2 moles of ammonia. Remember, the energy as a result of this reaction is released, that is minus 88 kilojoules per mole. This shows that the reaction is exothermic. When we were discussing energetics, when we were discussing energy from chemicals, that I told you that then I told you that when you have a negative lattice energy, a negative energy, that is this, as you can see, minus 88, or it can be minus 100, it can be minus 200, it can be minus like negative, like the negative value. I'm talking about the negative value. Whenever you see the negative value, so means that the reaction is exothermic. Okay. um, then these are the conditions for this reaction. The first one is we are supposed to provide 450 degrees Celsius temperature. Okay, 450 degrees Celsius temperature. And then we are supposed to provide 200 atmospheric pressure, and then we are supposed to like provide a catalyst, that is iron, for this reaction. Catalysts are catalysts are quite specific for the specific reactions. Like let's suppose in like for this reaction, the iron catalyst is the most suitable one. So you cannot use any other metal as a catalyst in this reaction until or unless, like let's suppose, transition elements can be used as a catalyst. So specifically, we can only use iron for this reaction. Okay, so you can say exclusive catalysts are basically exclusive. So particular catalyst for a particular reaction. Okay, this is a diagram for the Haber process. What we do basically, first of all, we are going to enter hydrogen gas and nitrogen gas from the inlet. Okay, this is the compressor. This is the compressor. And then they are going to into this reaction vessel. Okay, this is a reactor. This is also known as a reactor. This is also known as a reaction vessel. Okay, reaction vessel. Okay, in which you will see that nitrogen gas and hydrogen gas are going to react with nitrogen gas and hydrogen gas are going to react together to form ammonia. As you can see, this is the nitrogen gas triple bonded, and this is hydrogen gas, and this is ammonia. This is what? Ammonia, NH3. Okay, this bond is being broken down, and this bond is being broken down into this reaction vessel, and also the new bonds are going to be formed in the same vessel. So this is the most important part of this reaction. Okay, this is the whole, you can say, apparatus for this reaction, right? And let's suppose iron is used as a catalyst. As you can see, catalyst provides its surface to the reactants so that they can react in an easier manner and they can form a product in a limited amount of time. Basically, catalyst lowers the activation energy, catalyst increases the rate of reaction without its being used, and also it provides alternative pathway. Right? So after using iron catalyst, nitrogen is going to react with hydrogen gas to form ammonia. Okay, so ammonia is a gas. I have transferred this ammonia into this, you can say, container in which the ammonia gas would be converting into the ammonia liquid, and we can easily separate out ammonia liquid from this outlet, basically. Like, remember, the thing is that hydrogen gas and nitrogen gas, they would not be converting into the liquid form, because this is a reversible reaction. So when you would be transferring this basically the whole stuff is coming from this to this. This is the way from which they are going to convert from left to right. The whole thing, nitrogen, hydrogen, ammonia. This is a reversible reaction. So all the things would be there. Nitrogen is also, hydrogen is also, and ammonia is also. So the thing is that when you have provided a lower temperature to the ammonia, this is a coolant basically, right? So I'm going to provide the lower temperature to ammonia so that the ammonia gas can be converted into the ammonia liquid, and I can easily separate ammonia liquid from this outlet. But we have also other two gases that are nitrogen and hydrogen. They are not going to convert into the liquid form, but why? They are having high boiling point. They are having high boiling point. They are having high boiling point. I am providing special conditions, suitable conditions to particular reactants, to the particular species. Okay. So only ammonia gas would be converting into the liquid form. The rest of the things will not be converting into the liquid form because their boiling points are higher. So what they do basically, they reverse back, and then again they enter into this container. Then ammonia would be formed. Then I can separate the ammonia gas into the ammonia liquid. Then again hydrogen gas and nitrogen gas, they are not going to convert into the liquid form. Then they would be reversing back just like that. So basically this is the process that goes on to form ammonia, like this is the ray diagram which is going to tell you that how the ammonia is going to be, you can say, how the ammonia is going to be made through this reaction. So these are the reactions conditions, okay? But the thing is that I told you in the beginning of this chapter that there is a problem with reversible reactions. If you ask how, the thing is that this is a reversible reaction. I told you that they never form 100% product. They never form 100% product. You know, this is a reversible reaction. Once the product is formed, once the product is formed, so obviously the product would be reversing back to the reactant side because this is the nature of this reaction. This is the nature of this reaction. So I can say that only 30% ammonia is produced. Only 30%, only 30%, only. So let's suppose you have opened industry for ammonia and you want to make ammonia, you want to synthesize ammonia, you want to prepare ammonia and you want to sell. Ammonia is very important. You know, you can make nitrogen based fertilizers. You can make nitrogen based fertilizers from ammonia. This is quite important chemical, right? So uh, let's suppose you are industrialist and you have, yeah, like you have invested a lot of money, okay, and you have just purchased the whole material, the whole thing, the whole stuff, the whole, this, you can say, the containers, like all of the things that just you have purchased, and you have invested a lot of money. But when the industry is opened and then just the work has been started, and then you have noticed that only 30% ammonia is produced. Oh my God, how much money I have invested, and I'm only getting 30% of the product. How can I increase the amount of product? How can I increase the amount of product? How can I increase the yield of product? Yield means amount of product, right? The thing is that the leach at Lear is here to help you. The leach at Lear is here to help you out regarding this matter. That's why we did the conditions. If we are going to increase the concentration of reactant side, so the reaction moves forward. If we are going to increase the pressure of the reactant, so then we have to look at the equation. Which case is this? Some cases more moles of reactant than the product. In some cases, less moles of the reactant than the product. In some cases, the moles are the same. Then we would be deciding accordingly. Then we have temperature change as well. First of all, we have to see whether we have exothermic reaction or endothermic reaction. Okay, then we have used a catalyst. And I told you, catalyst has no effect on equilibrium, just it can increase the rate of reaction by lowering the activation energy, right? So these are the optimum conditions for 50 degrees Celsius. Pressure is 200 atmosphere and catalyst is iron. Now, the thing is that I told you, since the reaction is exothermic, since the reaction is exothermic, as the value indicates, okay, since the reaction is exothermic, what I told you that if you are going to increase the temperature of an exothermic system, if you are going to increase the temperature of an exothermic system, so the reaction moves backward. So the reaction moves backward. So why we are going to provide the higher temperature to this reaction? Since the reaction is endothermic, exothermic. Why? What's the reason? Providing heat is so much expensive. Providing heat is so much expensive. But the thing is that if we are going to increase the temperature, temperature is directly proportional to the kinetic energy of the particles. When the kinetic energy increases, so the collision between the particle increases, so the rate of reaction increases, right? So this is a most suitable temperature for this reaction. Yes, we know that this is an exothermic system. Higher temperature is not favorable for such reaction, but it increases the rate of reaction as well. It increases the rate of reaction as well. So that's why this is the best temperature for this reaction. This is the optimum temperature for this reaction. Okay. Until or unless it is not going to give you a good yield, it's not going to give you a good yield since the reaction is exothermic and you are going to increase the temperature. So this is not a favorable condition. But the thing is that the rate also increases. Rate also increases. That's why we are going to provide this much temperature, that is 450 degrees Celsius. It's too much. It's too much, right? So is optimum temperature for this reaction. Okay. Then I told you that providing temperature is so much expensive. So what am I supposed to do to increase the amount of product? I have invested a lot of money. What can I do? What can I do to increase the amount of product, to increase the yield of product? Then we have another option as well, that is pressure. That is pressure. So we have increased the pressure. As you can see the reaction, as you can see the reaction, we have 4 moles of reactants and 2 moles of product. We have 4 moles of reactants and 2 moles of product. We have decided that if you have such a system in which you have more number of moles of reactant and less number of moles of the product, so after increasing the pressure, the reaction will be converting into the forward direction. The reaction moves forward. We would be increasing, we would be having the more amount of product. The amount of product is going to increase. Okay. I would be getting the maximum yield. I would be getting the maximum yield after increasing the pressure. Since for the pressure, here is a favorable, you can say, environment. Like we have such a reaction in which only 4 moles of reactant and 2 moles of product. So which means that more moles of reactant and less moles of product. So if you are going to increase the pressure, so the reaction moves forward. So the reaction moves forward. This is the reason. This is the reason that we are going to apply the pressure as well. We are going to apply the pressure as well. Okay. Then 200 atmospheric is also optimum pressure for this reaction. And also, if you can imagine, if you are going to apply the pressure, if you are going to increase the pressure, so the particles would be coming closer to each other. So the particles would be coming closer to each other, right? When they would be coming closer to each other, so they would be colliding with each other. They would be colliding with each other. When they would be colliding with each other, so obviously the rate of reaction also increases. So, and remember, we cannot increase the too much pressure. The container may blast. Okay, there is a blast after increasing the too much pressure. 200 is the best pressure for this reaction. This is also optimum pressure for this reaction. So then we have added a catalyst as well. Catalyst is iron, which increases the rate of reaction without its being used, and it has no effect on the position of equilibrium. It only changes activation energy. Basically, it lowers the activation energy. So this is what the Haber process says. This is what the Haber process says. Anyone, any question, feel free to ask. Okay. Then we have contact process. Then we have contact process. Okay. Then we have contact process. So in this process, we are going to prepare sulfuric acid. In this process, we are going to prepare what? Sulfuric acid, basically. Can anyone tell me the formula for sulfuric acid? Yes. Can anyone tell me the formula for sulfuric acid, please? Anyone?
Sulfuric acid, right?
H2SO.
Sulfuric
H₂SO₄.
H2SO4.
H₂SO4. Exactly. Sulfuric acid is H₂SO4. So we are going
As the
to,
concentration of the
yes.
product is less, reactant.
No, basically, I want reactants. I want reactants first, right? I want reactant first. So in this process, we are going to prepare preparation of H₂SO4. Preparation of H₂SO4, and H₂SO4 is a sulfuric acid. Basically, it's a strong acid, right? It's a strong acid. It's a strong acid, okay? So,
It will increase as more heat will be absorbed.
yes. So, now the thing is that how we can prepare this sulfuric acid. So remember, first of all, we have a container just like that. We have a container just like that. First of all, we have a container just like that. Okay. Then just like that. Okay. And then someone is eating something, I think so. I think so. Okay. Keep. Please carry on. Okay. Then I'm also hungry, by the way. Okay, yes. Yes. So basically, um, first of all, first of all, first of all, I am going to provide the sulfur that is solid, and dry air, and dry air, and what? Dry air, and dry air. Basically, this is a furnace. Basically, this is a furnace. Okay, this is a furnace. So they are going to react together. Okay. They would be reacting together. They would be reacting together to form sulfur dioxide. So S plus O2 gives SO2. Okay. Okay. And then sulfur dioxide is produced. Okay. So basically, this sulfur dioxide is quite impure. This sulfur dioxide is quite impure. This is impure. This is impure. Okay. Then we transfer this sulfur dioxide into this container. So in this container, they would be reacting with more oxygen to form SO3. This is very important reaction. This is very important reaction. Okay, this is very important reaction. As you can notice, this is equilibrium reaction. This is equilibrium reaction. As you can notice, this is equilibrium reaction. Okay, so equilibrium reaction means that we have certain conditions. Obviously, this is a reversible reaction, as we have noticed in you can say Haber process. Only 30%, only 30% product was obtained through this reaction. So obviously this is a reversible reaction. We need more product. We need more product. So what the condition am I supposed to change to increase the amount of product? So that's why I'm saying that again, this is a reversible reaction. Again, this is a reversible reaction just like that. So certain conditions are required to increase the amount of product, So the conditions are, let me tell you equation first. This is 2SO2 plus O2 2SO3. Since the reaction is exothermic, this reaction is also exothermic. This reaction is also exothermic. And remember, these are the conditions for contact process. Number one, temperature should be 450 degrees Celsius. And then, you know, catalyst is added. Catalyst is added, that is V2O5. Vanadium 5 oxide, vanadium pentaoxide, okay? Vanadium pentaoxide. So when we are going to provide such conditions, so more SO3 would be produced in the presence of high temperature, and a use of catalyst is also there. SO3 is produced basically as a result of this reaction, and this is an equilibrium reaction. To increase the amount of yield, since the reaction is exothermic again, so higher temperature is unfavorable, not favorable. So why I'm going to give the higher temperature, that is 450 degrees Celsius. So the reason is the same. The reason is the same as, because the rate of reaction would be increasing after providing the temperature, and catalyst is going to increase the rate of reaction, and it's going to lower the activation energy. Okay, it's going to lower the activation energy, right? Okay, and then sulfur trioxide is going to react with H₂SO₄ to form this. Remember, this is called oleum. This is called what? Oleum. H₂SO₂. Then H₂SO₂ would be reacting with H2O to form H₂SO₄. Finally, basically, okay. Then obviously ammonia, sulfur, H₂SO₄ is obtained, so I can tape off H₂SO₄ from the bottom of the container. So right now, finally, the sulfuric acid is produced. Sulfuric acid is produced by the reaction of oleum with water. Okay, done. So these are the two reactions that are most important: Haber process and contact process. Right? Okay.